Okay, so let's start the first video of my YouTube channel, which is the introduction to the Riemannian geometry. And let's start with the first topic, which is what is curvature. Okay, so now I am following the famous book, which is Introduction to the Riemannian Geometry, is written by John Emily, the famous mathematician. Okay, so let's start with the first topic, which is the what is curvature. So basically, we all know, or we can say that we all have a basic intuition what is curvature, right? So let's start with the mathematical definition and let's begin some intuition. So if we have spent some time studying modern differential geometry with its intricate web of manifolds, submanifolds, vector fields, Lie derivatives, tensor fields, differential forms, orientations, and foliations, you might be forgiven for wondering that it all has to do with geometry. In most people's experience, geometry is concerned with properties as distances, lengths, angles, areas, volumes, and curvatures, right? These concepts, however, are so the purpose of this book is to introduce the theory of Riemannian manifolds, right? I hope that we all have gone through the Euclidean manifolds, but the Riemannian manifolds equipped with Riemannian matrices. So we are talking about smooth manifolds in Riemannian geometry, right? So basically, in this chapter, we are dealing with Riemannian matrices, smoothly varying choice of the inner products on tangent spaces, which allow one to measure geometric quantities such as distances and angles. Right. This is the branch of differential geometry in which geometric ideas in the familiar sense of the word come to the fore. It is the direct descendant of Euclid's plane and solid geometry, right? By the way of Gauss theory of curved surfaces in space. Okay, so let's summarize this that here basically we are dealing with Euclidean planes and solid geometry. So now basically we are doing these things in Euclidean geometry, but in our nature, nothing is Euclidean, right? Nothing is as ideal. So we have to bring that Riemannian geometry has an important role in that sense, right? So Gauss theory of curved surfaces in space are really very important in this chapter, and it is a dynamic subject of contemporary research, right? So, the central unifying theme in the current Riemannian geometry research is the notation of curvature and its relations of topology. Right, there are a lot of connections between topology and geometry, right? Basically, we can say that topology is the heart of geometry. We can at least say. This book is designed to help you the develop both tools and the intuitions you will need for an in-depth exploration of curvature in the Riemannian setting. Okay. So unfortunately, as of you who will soon discover an adequate development of curvature in the arbitrary number of dimensions required a great deal of technical machinery, making it easy to lose sight of the underlying geometric contents, right? To put the subject in the perspective, therefore, let's begin by asking some very basic questions. What is curvature? Right. At first, we have to be precise regarding the definition of the curvature, right? We all have a basic intuitions of curvature, but we have to mathematically establish the exact definition of curvature. What are some important theorems about it? So, it is very easy that if we will start reading about the curvature, then naturally a lot of theorems, a lot of corollary will become, right? In this chapter, we explore these and related questions in the informal way without proofs. The official treatment of this subject begins in chapter 2. Okay, so a brief introduction to the curvature, and we can say this is the basic motivation of studying the Riemannian geometry. Okay, so now let's start the Euclidean plane. To get a sense of the kind of questions Riemannian geometers address and where these questions came from, let's look back at the very roots of our subject. The treatment of the geometry as a mathematical subject began with Euclidean plane geometry, which you probably studied in secondary school, right? So, in our secondary school, we all are familiar with the Euclidean plane or Euclidean geometry. So all those things were contained in Euclidean geometry. Okay. So which you probably study in your secondary school. Okay. It elements are points, lines, distance, angles, right? We did those things in our schools, right? So basically all the points or all the topics was based on Euclidean geometry. Okay, and its most fundamental relationship, its congruence to plane figures and congruence if one can be transformed into the other by the rigid motion of the plane, which is a bijective transformation from the plane to itself that preserves distances. Here are a couple of typical theorems. So this is the theorem one, side, side, side. Actually, we did all those things in our schools, right? So let's recall all those theorems. Two Euclidean triangle are congruent if and only if the lengths of their corresponding sides are equal, right? And the theorem 1.2, which is angle sum theorem. The sum of the triangles of an Euclidean triangle is pi, right? The basically the sum of all three angles of a triangle is 180 degree, right? So as trivial they may seem, these theorems serve to illustrate two major types of the results that permit the study of geometry. In this book, we call them clarification theorems and local to global theorems. The side 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 SSS theorems, clarification theorem. Okay, so basically these are the all motivations of doing Euclidean geometry, and the angle sum theorem is a different shorts, but basically these theorems describes a lot of things regarding triangles, right? So local to global theorems. So those are the all old theorems we did in our school life. So after providing the basic facts about points, lines, and figures constructed directly from them, one can go to the study other figures derived from the basic elements, such as circles. Okay, so okay. So let's start with the theorem 1.3, which is circle clarification theorem. Two circles in the Euclidean plane are congruent if and only if they have the same radius, right? So then this is so easy, and then we can say that two circles are congruent if and only they have same radius, right? So nothing is new in that. So this is circumstances theorem. The circumference of an Euclidean circle of radius r is 2 pi r, right? These all the things we already knew from our school. Okay, so if we want to continue our study in plane of geometry beyond figures constructed from lines and circles, sooner or later we have to come to terms with other curves in the plane. An arbitrary curve cannot be completely described by one or two numbers, such as length or radius. Instead of the basic invariant is curvature, which is defined using calculus, right? And is a function of position on the curve. Formally, the curvature of a plane gamma is defined to be k gamma, which is the modulus value of the second derivative of that particular curve, right? Formally, the curvature of a plane curve gamma is defined by that form. The length of the acceleration vector, yeah, basically we can say that the length of the acceleration vector, right? And when gamma is a unit speed parameterization. Okay, so so those are the basic motivations of studying the Riemannian geometry, and we have started with the curvature in Euclidean plane. So basically, this much are the motivation for doing Riemannian geometry. So basically, we will go to Riemannian geometry by starting after Euclidean geometry, right? So basically, we have to construct a basic things in Euclidean geometry, then it will be really very easy to understand the Euclidean geometry. Sorry, Riemannian geometry. Okay, so let's stop the presentation here. So this much is enough to get a little bit motivation to study Riemannian geometry. Okay, so let's come with the next video or next part of this introduction to Riemannian geometry. Thank you.